Okay, Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. So today we proceed with the third technique of digital modulation, that is phase shift keying or PSK. The PSK is the digital modulation technique in which the phase of the carrier signal is changed from 0 to 180 or from negative 90 degree to positive 90 degree relative to the reference phase by varying the sine and cosine input at the particular time. So PSK signal can be represented by VPSK, where the VPSK T equal EC cos omega C T plus theta T, where the EC is the amplitude of carrier signal and theta T is either 0 or pi. 0 or pi phase in radian. So PSK technique is widely used for wireless LANs, biometric, contactless operation, along with RFID and Bluetooth communication. Okay, there are two types of PSK. Depending upon the phases, the signal get shifted. The first one is binary phase shift key or BPSK. Okay, this also called as two-phase PSK or phase reversal keying. In this technique, the sine wave carrier take two-phase reversal such as 0 and 180. So this is a two-phase binary or two-phase. So it's only have 1 and 0. So BPSK is basically a double sideband suppressed carrier DSBSC modulation SIM for message being the signal operation. Okay, the second type of phase shift keying is quadrature phase shift keying QPSK, and this is the phase shifting technique which the sine wave carrier takes four phase reversal. Okay, before this we have only 0 where is 0 and 180 degree, but for quadrature this is four phase. That is, we have okay, for this 4 phase it is 0 0. This 2 bit, 2 bit 0 0 0 1 0 1 1 0 and 1 1. So we have 0 90 degree, 180 degree and 270 degree. Okay, so this kind of technique are further extended, and PSK can be done by 8 or 16 value also. Okay, so this is the two types of PSK. So but for next slide I will start with BPSK first. Okay, so this is this is PSK spectrum. Okay, this is for BPSK. Okay, for the spectrum of PSK, the phase of the carrier is set to 0 degree or 180 degree. So for example here we have okay, this is the carrier signal. And this is information signal, AMT. Okay, this is the time domain, and This is frequency. Okay. For the frequency domain of the carrier signal, we have omega c here, and for the information signal, we have, for example, we have a signal of 10101. So the frequency domain, we have omega m, 3 omega m, and 5 omega m. Okay, after multiply, it's become, okay, for here, different with amplitude and frequency shift keying. For the phase shift keying, the phase is shifted. So for example here, this is 1 and then it's 0. So the phase is shifted here, and also from 0 to 1 also shifted here, and 1 to 0 is shifted here. So multiply both two, we have the frequency domain of this is like this, and the equation for PSK. Okay, we have the, okay, VPSK is equal to EC cos omega CT plus theta t. For the theta t equal to, okay, this is 0 degree, it's 1. For, okay, for example, okay, so 1 and 0, because this is cos, is will different for the positive and negative. So for 1, it's become positive EC cos omega CT, and for 0, it is negative EC EC cos omega CT. Okay. So taking Fourier series of bipolar signal, we have the VMT. Okay, for this bipolar, we have VMT equal, okay, this is the equation for VMT, and equation for the carrier from the local oscillator is EC cos omega CT. So after multiply together, we have the equation like this. Okay, we have the equation like this. So this is the equation for VPSK or VBPSK. And for the bandwidth, the bandwidth of PSK, okay, because we have the spectrum of PSK is like this, and the bandwidth is from here to here. So this is 2 FM. So the bandwidth of PSK is 2 FM, same as bandwidth of ASK. Okay, and this is the block diagram for the generation and receiver of PSK. So for to get the BPSK, the binary phase shift keying, it can be performed using the changing two phase of the carrier. Okay, we have here, for example, the information signal is 0, 1, 0, 1, 0, 1, and this one is 1, 0, and then is go through the level converter from unipolar to bipolar. So from here it changed to the same signal, but the amplitude is positive V and negative V. So okay, then this bipolar signal will go through the valence modulator, where this balance modulator consists of carrier signal from the oscillator signal. So this balance modulator will multiply the signal from information signal with the oscillator signal, and if the binary input is 1, okay, because we have binary bipolar here, okay, for the 1, the output signal will in phase with the reference oscillator. But uh, if the input is logic 0, the output is different phase with the oscillator signal, and then it's okay. And then the output of the balance modulator will go through the band pass filter. That's this band pass filter allow in the range of the required signal, and the output is VPSK. Okay, for the receiver, we have two kind of the VPSK signal. That is the in phase signal and different phase. So for the PSK signal, is the VPSK will go through the multiplier. This is multiplier, and the signal will multiply with the FC and the output go through the low pass filter, and we will get back the VMT, the real digital signal. And for the noise in PSK, the possibility of error for the PSK signal at receiver, the equation is PE equal 1/2 ERFC square root of EB over NO, where the EB equal EC squared T over 2. Okay, so this is the equation for the noise in PSK. Okay, let's try this example. Okay, calculate the probability of error for PSK system with the EB equal 4.55 times 10 power of negative 3, and NO is equal to 2 times 10 power of negative 4. Okay, equation for PE for PSK is 1/2 ERFC square root of EB over NO. So we have okay, EB is 4.55 times 10 power of negative 3, and NO is 2 times 10 power of negative 4. So we will have 1/2 ERFC 4.77. Okay, For ERFC, we need to refer to the table of ERFC, and we will get ERFC for 4.77 is 1.52 times 10 power of negative 11. So the answer of this error for PSK is 7.6 times 10 power of negative 12. So this is the final answer. Okay, so this is the last slide for PSK. So the advantages of phase shift keying is this phase shift keying is immune to noise. It has the same bandwidth with ASK, and it have multi-level PSK. That is, we have BSK, BPSK, and QPSK. Okay, I will explain about this later in the next lecture. Okay, that's all for today. Thank you.